So I actually wanted to, so every time when we do the class, like in class, everyone can follow along on their laptops usually when I do the problem in the software. So are you guys also, do you want to do that this year or just see as I work out the problem?
So my suggestion is whoever is ready should follow along. So let's first ask, how many of you have actually installed, or let me ask, who has actually installed it?
I
Say
did.
something. Okay.
Okay,
I did
Any
too. I installed it too.
Okay, I see.
about how?
Okay, so let me see. Okay, so there is enough, maybe more than almost a little bit less than half. So
Okay.
I
So
would
I
say,
would suggest, like, while we are setting everything up, maybe just log into the Ingman lab using your VMware client, because it takes a little while. Like maybe it will take 5 minutes or so
yeah. So
to connect.
Apratim, you are a co-host now, so
Okay.
you can
So I
share.
can, yeah, start
Yeah,
sharing.
let's get started because there's a lot of stuff to cover. And while Apratim is setting it up, I just want to remind everyone that next Tuesday we have the next assignment. So it's not a lot of time. Just keep track of your time. I know everyone's busy, so but don't forget this is a very important assignment. And again, message us, Apratim or me, on Slack if you have any questions or if you need any help. We are both available. Okay, I'll monitor the chat, Apratim, but I might.
Okay. So I'll just remind you guys that if you have the VMware client installed, you should just start running it and log into the College of Engineering server using your KidLab user account and password. And then once you're in there, you'll come to this screen. So just select any one of the
let me just remind everyone that the instructions for this are already posted on the class website. So you can definitely read through it. And if you have any problems, just message Apratim. He's on Slack. He will help you. Okay, go ahead, Apratim.
So, so all those who have come up till here, can you give me like a thumbs up like you did last time? So I know. Hello?
Yeah, they're doing it. Yeah, so at least a few
so my
of them.
Zoom is sort of like stuck.
That's fine. I'll monitor it. So it looks like
okay, yeah. Now, so my Zoom is lagging. I don't know. Maybe I have too many things running on this computer. Yeah. Okay. So and then once you so just select one of these pools, and it will open up a Windows virtual machine. So I have windowed mine. So this is my Ingman Lab connection, basically, right? And so once this starts up, just type Comsol and select the this one, the class kit license, multiphysics 5.5. So that takes a little while to get started. So while that happens, so this is the problem that we are going to solve. Let me close up a few background programs. My computer is running a lot of stuff, so maybe that's why it's a little bit slow. Okay, so again, let me know once you've started Comsol. Maybe we can wait like 5 minutes, and this page will come up. So again, give us a thumbs up when you're up till here. Okay, I see one of you is already up to this page. So this will take a little while, like because Comsol takes a long time, so a little bit time to get started. After that, I think it will flow nicely. Okay, so while that gets started, so let's look at the problem that I'm going to solve. It's a simple problem. So again, like Dr. Menon said.
Apratim, 1 second. So let me just remind everyone, we posted the instructions last week. So make sure you try to monitor the announcements to get prepared, because that will really help you learn significantly more if you're actually able to do it along with Apratim. So let me just reiterate that, okay? And for the Synopsys software, we are trying to set up the network license. There's been some technical difficulties, but we'll hopefully try to get it done in the next day or so. So you should be able to access it. If not, I'll also let you know. Go ahead, Apata.
Okay. So yeah. So one more thing, I think this will also be recorded and put on the website. So last year, a lot of students actually did use Comsol's ray tracing for their projects, and they reached out to me later on with some specific problems that they had, and I tried to help them solve it. So yeah, this year as well, you guys can do that, and I'll be happy to answer all the questions that you have. So one thing to get started, Comsol can simulate many different types of physics, but today we are just going to focus on the geometric optics module of Comsol. But you can use Comsol to simulate many different things, and I encourage you, if you have applications in your respective projects, to definitely go through what the software can do, and hopefully it'll be helpful to you for other projects as well. So for this tutorial, I've selected a fairly simple problem that I want to simulate using Comsol. It's a two-lens system. So as we have already learned from the geometric optics lectures in the last few weeks, that if you place a point source um, in the focal plane of a planar convex lens, light rays are going to diverge away from the point source. And when it goes past the lens, these light rays are going to get bent by the lens in such a manner that if the point source is placed at the focal length of the lens, the rays will become parallel to each other. And then again, the second part of the problem is what happens to parallel rays when they interact with a planar convex lens. They basically come to a focus at a point which is located one focal length away from the second lens. So the diverging rays become parallel rays after interacting with the first lens, and then the parallel rays become converging rays and come to a focus at a point, right? So this is what we are going to try to model using Comsol. So I'm going to show you how to interact with the different modules that are there in the software, how you can use the geometry and some part builders to um, make these lenses and then define your source, and then use the ray tracing aspect of the software to trace out the way these rays are going to interact in the system. Okay, so I think by now a lot of you should have this screen over here. So this is the default screen that you see when you open Comsol, and you can use the model wizard. So I'm going to go slowly so you can also follow along with what I'm doing. And I've windowed my Ingman Lab connection, so maybe you can also do that and keep the Zoom video on another window or side by side so that you can watch me and follow along. So first I would click the model wizard, which gives me a selection of different types of models that I would want to do. So 3D, 2D, and so on. So for this purpose, I'm going to do a full 3D simulation. So our lenses will be in complete 3D and so on. So I'll click this, and then it will ask me to select the type of physics that I want to simulate. So you can see there's a bunch of different things that you can do. And in the optics module, you have both the ray optics and the wave optics. Remember that ray optics is what we're going to deal with, otherwise known as geometric optics, right here. And wave optics is something which is more useful when your structures have dimensions which are closer to the wavelength of light. So I used wave optics simulation module of Comsol extensively for my PhD studies, where I was dealing with structures in the order of few nanometers, which are in the order or even smaller than the wavelength of light. But for now, all the lenses and stuff that we're going to model will have dimensions of few inches, like in millimeters and so on. So we'll select geometrical optics and then click add. Okay. And then we click study. And it will ask us to select the type of study we want to do. For this case, we'll do bidirectionally coupled ray tracing. And you can see a short summary of what these kind of studies refer to, what they do specifically and so on. And yeah, you can go through them and read them and stuff. And then I'll click done. So using whatever we selected here, Comsol is going to start up the basic layout. So I'm going to wait for a little while and give me a thumbs up when you're up till here. Then I'll go forward. Okay, I see one. Maybe I'll wait a few more. And ask me questions if you missed anything, just shout out your question instead of writing on chat. I think that's just easier for today, at least.
All right, I'm so sorry. I missed the part where you open actually.
Okay.
That software. Can you show again?
You mean from the beginning? So do you already
I'm
have
so
the,
sorry. Yeah.
no, that's fine. So you have the Windows virtual
Yep.
machine
Yep.
running?
Yep.
Okay, so then just type Comsol in the search field and select class kit license Comsol multiphysics
Okay.
5.5.
Okay.
Okay, and that should show you the splash screen with Comsol's logo.
Right on.
Do you see that?
Yeah, I'm opening right now.
Yeah.
I opened the MATLAB. Let's see.
Okay. Yeah, so another interesting feature that Comsol has is that you can run it as a server with MATLAB. So you see Comsol multiphysics with MATLAB. So a lot of the times if you want to automate aspects of your program, so in this case we'll use the GUI to make one program and solve it, one problem and solve it, right? But in some cases you might want to run different versions of your problems with different parameters, and you want to automate that process. So you can build a front end in MATLAB and then call Comsol as on a server, and basically use your MATLAB program to continuously run Comsol in the background and move data back and forth. So this is what I used to do when I was working on my doctoral project. So I use the Comsol with MATLAB server option, and you can explore that if you want, but that's not something that we're going to deal with today.
Thank you.
Okay, so Kenneth, do you have Comsol running right now? Or?
Yeah.
Okay, so do you want me to just go over the last few steps? I mean, we have some time.
Please.
Okay, so yeah. So do you have this page open right now? This screen?
Okay, 1 second. It's a little slow right here. I'm sorry.
Sorry?
No, my computer is a little slow because it's getting the firmware, and I'm depending on my internet. My internet's not the best, but
Okay.
I'm getting there. So console documentation. Okay.
While we're waiting, I just want to reiterate that you will be expected to do some careful simulations of your innovation, I believe, for assignment 4. So it's quite important that you know how to do either this or what we will talk about on Thursday. Of course, or you can use alternatives as well, but these are the two good options that are freely available to you.
Yeah. My thing is open. You can keep going. I'll get it.
So just, yeah. And so what I did was I selected this model wizard option. Then I selected 3D because I want to simulate this problem in 3 dimensions. And then I went to optics module, ray optics, and geometric optics. And I did add. And then I went to study and used bidirectionally coupled ray tracing. And then click done. Maybe I think I ran 2 versions. Oh, that's not good. Oops, I think I made some mistake and closed Comsol altogether. Sorry, my bad. So maybe
It's okay.
yeah, wait like 2-3 minutes for it to start running again.
If you have any questions, it's a good option to ask. Also, I will point out that, of course, you won't be asked to do any software-based simulation in your midterm exam. this is purely important for your project and also, something which will be very useful for you.
Yeah. Okay. So yeah, I'm back to where I was. So at this point, I'd like to just save the model. Um, just save it somewhere on the local disks because I'm on the Ingman server. I'm just saving it on in my documents folder right now. Probably not a good idea in the long run, but for now is okay. Later on, if something happens and your program crashes, you don't want to lose the progress. It has happened to me once or twice, so make sure you don't forget this step. So another good thing that I can quickly show you is that if you're logged into your Ingman Lab servers, I forget exactly how I did it, but I think before when I was using it, I somehow managed to connect my local drives on my laptop with the Ingman server. So I can also access the files which are on my laptop right now through this server on a Windows network drive. Maybe something you can look into if you don't want to store your simulations on Ingman Lab servers in case something happens. For now, it's fine. Okay, so now that we are in this page, so let's look what we have here first. So in the right-hand side, there's this graphics window, which is going to show you all the different components that you're going to put in as you go through solving this problem, your lenses, your rays, and so on. And over here, we have these different tabs with different options like definitions, geometry, materials that you can define, and the type of physics that you want to work with, the mesh, and etc. But first, what we are going to do is, let's see. So first, we are going to go to this model builder tree. So this has all the things that are related to this specific simulation. So you see, we saved the model as model 2, and if I just minimize this, so this is the entire model. So underneath it, in the form of a tree, you have all the different things that you can define, right? And so first, what we are going to do is we are going to go into geometry and first define our units. So here in geometry, we see the length unit is in meters. I want to change that to millimeters. And that would be the default geometry for all the different types of values that I enter, unless it's specified. So in this case, remember, I'm working with, say, a lens which is 1 or 2 inch diameters, or in other words, 25 millimeters or 50 millimeters. So I want to specify the length unit completely as millimeters, and then I can just give numerical values to different variables that define what the lens dimensions are and so on, or the distance between the lenses, stuff like that. So length unit is millimeters, angular unit is fine, in degrees, that's fine. Okay, so this is the first part that I would do. And then I would go to parameters and define certain parameters that I'm going to use for constructing my model. So how does these parameters work? So suppose you can make a lens in this program, and you want to specify the different variables like radius of curvature, edge thickness, and so on. You can hard code those in, like put in values for radius of curvature being like 12 millimeters or so on, or you can predefine certain parameters here so that you don't have to go in later on to all the different places where you called those parameters and change those values. Instead, you can then later on, it's like just defining a variable. Instead, later on, you can just go to just this place here and change the value of that parameter, and it will update wherever that parameter has been called throughout the entire model, right? So how this table works is you just basically type in something, but don't type in right now. I'm just showing you. So you just type in, suppose f focal length or something, and then you put in a value and a description and so on. But there's another way to do it. That's by putting in a file which already has certain values that you have predefined in that file, right? So that option is here, which is the load from file option. And we uploaded a couple of files on the class website, if you remember, which has the certain values of these parameters that we are going to use, like so. So this is one of the files. and this was one of the files. So did you guys download these? If not, then they are still located here. They are also on Canvas. I've mirrored everything of the class on Canvas as well, but the files are here and here. So you can download these text files and save them on maybe in the same folder that you're working on for this problem. So again, can you give me a thumbs up of all those who have these files, or any questions up till here before I go ahead and load the file into this program? Okay, I see one person.
I got to where you are. I don't have the files yet. So,
Sorry?
no, I say I got to where you are. I just don't have the files yet, but just keep
Oh,
going.
okay. Okay. But do you see the links?
Oh, I do, yes.
Okay. So suppose if you, I think we'll just use one of the files here. So what I did was actually this tutorial that I'm doing, I adapted it from one of the examples that's there on Comsol's website. And so these files were already there. I didn't change the names and stuff like that, but you'll understand how the files work and then you can change them yourself. So I just used the files from there, but I adapted the tutorial to make it simpler to solve our problem that we are dealing with in this case, which is this one. And on the Comsol example, there's some bunch of other stuff, but not terribly important for us. So you can see all the different kinds of stuff that's in this file is the diameter. So suppose you see it's lens1 parameters. You can see the diameter of the lens has been specified, the radius of curvature of the lens has been specified, edge thickness has been specified, and so on. And there's other stuff like the power of the source, the wavelength that we want to simulate for, etc. Again, the diameter of the lens and all this stuff is here. Then distance between collimating and focusing lens. So in this problem, the first lens is called the collimating lens because it takes diverging rays and make them parallel. In other words, this is called a collimated beam. And the second lens is called a focusing lens because it does the opposite. It takes parallel rays or a collimated beam and brings them to a focus at a point. Okay, so I think I'll use this second file, which is named thermally induced focal shift parameters. We are not going to work with the thermally induced focal shift, but we'll use the parameters which are here that define what the lens dimensions are, the distance between the lenses, the wavelength of light, etc. So I'll go back to Comsol and I'll do load from file and select the thermally induced focal shift parameters and click open. So you see immediately it loads all the different values that were there in this file. We can check this. Let me close this. So we can check like it has all the different values and they have been imported correctly. So you can use one of these files as a template and generate your own file. That's the easiest way to do so that you don't mess up the format or anything like that. But it's basically, it goes as name of the variable, then expression or value, and then what the description of the variable is. So I usually just copy this file and then change the values to whatever I want them to be. Okay, so how many of you guys, if you guys are still following along, are up till here? Okay. Okay, that's good. All right. Seems good. So maybe then let me go forward. Okay. So in the geometry, now let's add a geometry item to this problem. So one way to do this is you can make your own geometry from primitives, like using a block or a cone and stuff like that, cylinders and spheres. Or if you are working in a 2D plane, you can define their 2D analogs like a rectangle or a circle and so on. And otherwise, there's also a way to import certain geometries that are already pre-built into this software. Let me see. So yeah, so go to, so same things you'll see, all these different um, items that are here, like definitions, geometry, materials, physics, mesh, are also located on the tabs over here. So definitions, geometry, materials, physics, mesh, and so on. So you can use either one of these to add certain things to your programs. So go to geometry tabs. Sometimes I don't find something here, I look here and then, or sometimes you'll find them here, but they should all be at both places. So then click on parts and go to part libraries. Okay. So in part libraries, you have Comsol has already used some kind of a 3D software to pre-make certain types of geometries that we can directly import into our program. So let's look at what we have for a ray optics module. So if you go to ray optics module, and remember we are working in 3D, so select 3D, you have all these different types of things that you can import in, like apertures, lenses, and so on. So we'll work with spherical lenses. So we go to spherical lenses, we see there's a bunch of different options there as well. And we'll work with plano-convex lenses, right? So plano-convex lenses in 3D. So we go to spherical plano-convex lens in 3D. And you can see for each and every parts that are available, they have this small little diagram and description of what these kind of, this particular item is. So you can see the 2D cross section matches very nicely with what we expect it to be. This is the 3D representation. So suppose if you want to use a concave lens, the curvature is bent inward, and there's, let's see, there's mirrors as well. So parabolic concentrators like this. So maybe, I don't know if some of you are working on projects which require you to concentrate large amounts of solar light at one point. The parabolic concentrator is something that you can use. Annulus, these are irises or beam blocks, which limit the size of beams and so on. Then you have beam splitters. And so a bunch of different things that you can work with. So today we are going to select the spherical plano-convex lens 3D and do add to geometry. Okay. So again, what did I do? I went to part libraries, ray optics module 3D, scroll down to where spherical lenses are, then spherical plano-convex lens in 3D, and add to geometry. So when you ask it to add this part to your geometry, it will ask you to what kind of definition do you want to use for the lens? Like what kind of, what dimensions of the lens do you want to define? So here.
So where is the part library? Once again, I'm sorry.
Yeah, go ahead.
Where is the part library?
Oh, okay. Yeah, let me just redo them. So close. So what I did was I went to this geometry tabs up here, and then I went to parts, and then part libraries. Did you find it?
Got it.
Okay. So part libraries, and then inside part libraries, ray optics module, 3D. So I went to ray optics module, then 3D, then inside 3D, I went to spherical lenses and spherical plano-convex lens 3D. And I did add to geometry. So then it will ask me what kind of dimensions of the lens do I want to define. And I want to specify the radius of curvature and edge thickness. You can do either one, it doesn't matter. Just make sure that that's the parameters that you are also defining in the text file or in the first parameters fields. So the way I have set this up is using the radius of curvature of the plano-convex lens and the edge thickness of the plano-convex lens. So using those, I'll do the same thing here. So I will specify radius of curvature and edge thickness. You could do different other kinds of parameters, but let's do this for now and click OK. So it will add the plano-convex lens here. See, it's added a spherical plano-convex lens 3D one over here. And then it has all these different values, right? For radius of curvature, edge thickness, diameter, and so on. So you can change these values here as well. So for the diameter of the lens, 50 millimeters is fine. For the radius of curvature, so I'm just going to plug in some values that I already know would work because I prepared based on those values, but you can change them and see what the effect it has on the model and so on. So for radius of curvature, I have 68.8 millimeters. And for edge thickness, I have 3 millimeters. That's all that I'm going to change here. Okay, and you see they'll all get updated over here. Okay, so what are these three? So local optical axis, the X, Y, and Z components, it tells me basically which direction I want. So this is in 3D, right? So X, Y, and Z, X, Y, and Z. So which direction or which orientation do I want to put the lens in? So what we are going to do today is we are going to have all our elements placed in the ZX axis while the rays propagate in the Y axis. So in Y, I will put 1 or -1, doesn't matter for now, and everything else is 0. So let's try it out. So if you do then build selected, it should build your lens. Okay. So now that we have something in the graphics panel, let me explain a couple of different of these buttons. So this is zoom in, zoom out. This is zoom to a specific location that you can select, zoom box. This one is zoom extend, so it just zooms out to the entire model. This is default view, which it is already set at. And if you want to see specific planes, so this is your XY plane. So you see Y axis pointed this way. This is your YZ plane, and this is your XZ plane, right? So let's see what happens if I change one of these parameters. So suppose I want to make a lens with a smaller radius of curvature, right? So I'll just change this value over here, maybe do 20 or something, and then do build selected again. Oops, sorry, maybe that's too small. So you would have to adjust it so that all the other parameters are not messed up. So maybe let's do 35 or something. So you see the lens became more bulged because the smaller radius of curvature. And if I then increase the radius of curvature to say 100 or something, you'll see it becomes flatter. So yeah, like that. I think what we were doing in this case is 68.8. Okay, so right. So you should have, if you followed up till here, you should have one lens like this. And okay, so let's see what happens if we change these values. So suppose I want -1 or something like that, and 0. So see, it just flipped the lens. It's now in the different orientation. So -1 and 0. Yeah, see, it'll flip which axis the lens is in. So just do, we can just select one and just stick with it for now. So these are the parameters that we are using today. And give me a thumbs up when you have at least one lens in your graphics window. Okay, one person has it already. Two people have it. And if you're stuck anywhere, this would be the time to shout out your question.
Hey, do you mind going over the text? How do you get the text file there again? I have the text file. I missed the part.
Oh, okay. You mean loading it into, how do I load it into Comsol?
Yes, please.
So you go to parameters section
Okay.
over here, and then this tiny open folder button. So load from file, and then select your text file. So in this case, I selected the thermally induced focal shift. You can name it whatever you want.
Gotcha.
I just kept the same name, whatever it was called before. And just select and just do open, and it will load all the parameters.
So right click on the parameter one and load from file.
Yes. Do you see it? So parameter one and then
load from file. Okay, got it.
yeah. Okay, did it work?
Yeah. Yep. Thank you.
Okay, so yeah, so we are up till here. We have one lens here, and we want to position this lens as well. So yeah, so what we do is we want to we want to set this up like this, right? So we have certain distances that we want the rays to be at, and what we have done is we have specified these distances before inside these files, right? So we want to move this lens to a specific location, and the way you do that is by entering a certain value in this section, the position and orientation of output. So the output in this case is the lens, and you want to displace it, right? So you suppose, let's see what happens. So suppose in the y-axis, because the lens is oriented, so the optical axis going through the lens is the y-axis, right? Suppose I want to move it 10 millimeters in the y-axis. Let me just type 10 and do build selected. So it moved 10 millimeters in the forward direction. Or if you want to move it minus 20 millimeters, so again, do build selected, it'll move back. So what we want to do is we want to type in minus dis over 2 and do build selected. So dis over 2, we have defined the value of dis as the distance between the collimated lens and the focusing lens, right? Which is this distance basically. So half that distance, minus half that distance is where the first lens should be. So that's that. And this is the good thing about using parameters. If you want to change what the absolute value of dis is you just change it here and it will get updated throughout the entire problem, all your different models. So I did minus dis over 2. So the lens got moved back. Again, I can re-click the YZ button. So it shows me, it just recenters it in the graphics window basically. Okay, we don't want any rotation or anything like that. So now we have the first lens, we'll make the second lens. You can do it in a similar manner, or I can show you another way to do it is by using certain transforms that are available. So if you go to, so one quick way to do it would be to just duplicate this lens, mirror it, and place it somewhere else along the optical axis, like move it forward. How do I do that? I go to geometry tabs and then click transforms. And in transforms, I select mirror. So if you click, so again, geometry tabs, transforms, mirror. So once you click mirror, you will see this mirror one function appear underneath your geometry section, okay? Then what you have to do is for all of these different types of transformations, what you'll see is you'll have an input object. And in this case, the input object is going to be this lens that we have already created. And it's going to create an output object by imposing the transformation on the input object, right? Suppose I want to do something like copy. So if I click copy, okay, so because I didn't do anything, let me just delete the mirror because it was waiting for an input. So I do copy, you'll see the same thing. You'll have a box for input object. You can input the lens again. And then if you do build selected, it's going to copy the lens. But in this case, we are both going to copy it and mirror it, right? So let me delete the copy and go back and add the mirror. So mirror. So in input objects, what you do is just click the lens. And remember, so for all of these different items that you input, it has this tiny variable name, like our lens has the name PI1. So if I click this, you'll see PI1 has now become the input object, okay? Now I want to keep the input object. So sometimes the mirror one, if you don't do this, it's just going to mirror it, but delete the input object. No, I want to keep them so that it also duplicates it. So I have two lenses. So I'll check keep input objects. Okay. Now point on plane of reflection is what point on the plane of this lens do I want the reflection to happen? That's fine. So everything is 0, 0, 0. So it's all aligned to the first lens. And then where do I want the normal vector? So where do I want the reflection to take place? So in this case, I think I have to do -1 so that it's just flipped along the y-axis and everything else remains 0. We can check. So let's just do build selected and then do zoom extents. So you can see the entire problem. Yeah, so it worked. And this is the 3D view. You can already also use your mouse to move around in 3D and then re-click the default view to go back to default. So let's see what the other, what these parameters do. So if I do -1 in y-axis, what it did was along the y-axis, it created a reflection of the lens, first lens. So suppose, so again, you don't have to do this, just see what happens if I do say -1, -1, -1. So it should create the copy at 45-degree angles, right? So just, it's just a simple vector geometry. So yeah, so it created the copy in this direction. Now if I add, suppose a translation of 100, 100 is too much, like 50 millimeters in Y. So it's going to move it 50 millimeters in Y. Suppose I want to add 25 millimeters in X. It's going to move it again in X. And then suppose I want to rotate it. So I add a rotation in Z axis. It's going to rotate it, see? So it rotated it. Okay, so I don't want any of these. So because our problem is just everything is aligned to the optical axis. So I'll read 0, 0, 0, then 0. Yeah. So this is what we want, right? And I want to use the YZ axis view because it resembles the 2D geometry view that I've drawn. And that's how you get your second lens. I'll wait and let me know once you have your second lens. In the meantime, I'll just check with my notes to see if I'm not missing out anything. Yeah.
I'm sorry, I am where you are. Can you repeat one more time how to get the second lens?
Did you add the mirror one transform to your
Yes.
geometry one?
Yep.
Okay. So then what would happen is your input objects, this should look like green. Do you have this? Like, so that it's enabled basically.
Okay, I don't have that part. Yeah, I
So
haven't.
click mirror one. If you click mirror one, this window will update to mirror settings, the settings for the mirror.
Okay, I'm there.
Okay, so now you see your input objects box, right?
Okay.
And this should be green. If not, click it to make it activate selection, like make it green.
Okay.
Then click your first lens and it will add the lens PI1 here. And then you just input these values. So 0, 0, 0 for point on plane of reflection and 0, -1, 0 for normal vector to plane.
Okay.
And then just do build selected. So once you do that, you should have your second lens. So if you're already zoomed in, remember you won't be able to see the second lens. So always go to default value, default view, or do zoom extents. So suppose you're like zoomed in and looking at just the first lens, you'll see, oh, I can see where is my second lens and so on. So always do zoom extents so it shows both the lenses,
Let me see.
or a default view.
Okay. Click right here, got my mirror, and 0, -1, and 0.
And then do build selected over here on top.
Okay, right on.
So you have both the lenses?
Yep.
Okay, others who are following along, do you guys have it too? Then I can go forward. Okay, so I think most of them have, most of you guys have. Others who are following along, I think if not, let me know or I'll come back and stop or stop. Okay, so now we have two of our essential components, right? So we have the two lenses. Only two more components need to be added. One is the source and one is a plane at which I want all the rays to come to a point at the focus. So let me do that first. I will add a work plane. So the way I do this is I go to geometry and I click work plane, which is shown over here. Again, go to your geometry tab and click work plane. Okay. So once you click work plane, it's going to add a work plane, WP1, underneath your geometry branch in your model tree, right? Then you click the work plane and it's going to bring up the settings for the work plane. And we do plane definition. So we want to first tell Comsol where we want the work plane to be. So you see the work plane has already been introduced in the graphics window, which is here. If I move it in 3D, I can see there is a work plane over here, right? But it's not oriented in the correct direction. It's inside the plane of the optical axis. I don't want that. I want it to be oriented in the ZX axis or XZ axis. So I'll just select ZX plane, and now it's oriented in the correct direction. Okay. And then I want to, in the Y coordinate, I want to move it in the Y axis so that it's positioned behind the second lens, like I've shown it over here, instead of in between the two. So let's see, I can type in something like 50 millimeters and do build selected, and it's going to move back. That's one way to do it. Or like I did previously for the lenses. So these parameters, I can take from these parameters and input a certain value, and the work plane would get located over there. So what I do is click work plane again, and in this case, we are going to do DIS over 2 plus TC plus BFL. So this is the back focal length of the second lens. And then I do build selected. Again, see, it vanished. So you'd think like, where did it go? I cannot see it. So instead, again, do zoom extends, and you'll see it's been moved back further. So you should have this work plane located here. Let me check something. Yeah, that looks good. So yeah, just do up till here and then give me a thumbs up, so then I can go forward. Okay. All right, seems that we are going well so far. So this is the work plane right now, and what we are going to do is introduce certain geometry inside the work plane on which we can do certain calculations. So the work plane is like, it's an abstract plane, like it tells you this is where all the calculations are going to be made. Now you have to select an area over which you have to select, you're going to take your output rays from, and so on. So that's what we're going to do now. But first, let's just save it till here. So if anything goes wrong, our progress is not going to disappear. So just click save once. Okay. So then after you've saved your work up till here, underneath your work plane branch, you'll find this plane geometry, right? And so click that, and in the once you click it, see your work plane options are going to change. So when you had clicked work plane over here, it was going to give you different options by which to create the plane. Now if you click the plane geometry, it's going to update and give you certain options which are related to the type of area that you want to put in over here. So locate your primitive section and click in square. So it's going to introduce a square area over here, and we are going to make it a 2 millimeter side length, because all the rays are going to get focused to a tiny spot. So there's no need in increasing the size of this, because the larger you make all these different objects, the more time or more computationally intensive it's going to get. So 2 millimeters, and do build selected. So it's going to create this tiny square over here. And also one other thing that we have to note is for the position, we are going to make center so that the square is located at the center. Right now it's at the corner. So see, if you look at 0 and 0, the square got made at the corner of where the 0, 0 is. Now if I update it to center and do build selected, it's going to move, and the center of the square is going to be located at 0, 0. Okay, that's what we want to do for now. and then I'll just click build all and go back to default view. Sorry, so click geometry and go back to default view. Okay. And then do build all. So if I do zoom extents, there's our work plane. If I do YZ axis, our work plane is over here. Okay. So now we have 3 components done. So again, I did build all in geometry and that built the work plane. So I have 2 lenses and a work plane. So I have 2 lenses and a work plane. And last thing to do is put source. So I'll wait a few minutes here as I refer back to my notes. Okay, so a couple of things that we have to add before we go to the source is let's go to this, yeah. So right click your definitions and click variables, okay? So it's going to, so we are going to add a couple of variables over here, which is nothing, it's very simple. We are just going to define the refractive index values of the materials of which the lens are going to be made. And the way you can do it is, again, you can hard code it in later when you define the material of the lens, or you can define certain variables over here and then call the variables later inside the lens materials. So we do what I did was right click definitions and then click variables, right? Right click definitions and variables. This basically, it means you're defining a variable. And then that's going to add your variables branch underneath your definitions, which you see over here. And make sure entire model is selected. And then what we are going to do is we are going to add certain inputs here. So n_r, that's the real part of the refractive index. And we are going to define that as n0. So n0 we defined in our text file as 1.45, real part of the refractive index. And 1.45 is close to what you have as the real refractive index of glass. So in the geometric optics lecture, what we learned was, if you remember Snell's law, that there's one value of the refractive index, right? N or N1, N2, so on. But in reality, refractive index is a complex term. So it has a real part and an imaginary part. For most of the materials that we are dealing with over here, the imaginary part has a very, very tiny value, and the imaginary part basically contributes to how much light is going to get absorbed within the material of that, within that material. While the real part tells us how much the light is going to be bent by that material. Suppose for glass, you have a real part of refractive index. It's going to tell you how the lens made of that glass is going to efficiently bend the light. And the imaginary part is going to tell you how much of the light is going to be absorbed in the glass. So in most of these cases, the absorption is pretty low because glass is nicely transmissive and so on. But I'm going to put this down anyways, because the model in Comsol is going to ask for the value. So I'll put N0 over here and I'll add like a very tiny value. So like what I did previously was 3 times 10 raised to minus 8, which basically means it's almost close to 0. But sometimes if you add 0, sometimes the program runs into some problems. So it's better to add like a very tiny value for such kind of materials. But there can be other materials which are absorptive, and you need to find out what the absorption value for those materials are and put those for the imaginary part of the refractive index. Refractive index doesn't have any units. And if you want to just make a note, write down a real part of refractive index and imaginary part of refractive index. Okay. Okay, come up till here. And then what we are going to do is we are going to click on definitions and go to non-local couplings and choose integration. Okay. What this is going to do is make sure that all of these different components have been taken into account when it runs through the solver. So do that. Okay. I'll wait till here. Okay, and then select all. So okay, so yeah, just let me just check. Yeah, so okay, so if you have up till here like definitions and then integration, what we are going to do is add all the different domains that we made, right? So add everything. Okay.
Apratham, where do you get the integration?
So you, where are you up till here? If you are in the variables,
Yes.
just click definitions.
Okay.
And then non-local couplings and then integration.
Okay, got it. Thank you.
Okay, and then we are going to add one more definition, which is this is selection defined by explicit set of geometric entities. So we are going to click explicit and then just select all domains. So it's going to select all the domains in selection. So just add these two. So definitions explicit, and then add both the domains, so that when it runs through the solutions, it doesn't ignore any of the domains that we have already defined. And at this point, I would just save it once more so that we don't lose anything. And the last thing that remains to be done is to define the source, right? So we'll now click on geometric optics and define the source. But before defining the source, do you guys have any questions? And this is pretty interesting, this part now. So if you have any questions, or I'll wait like 2 minutes, 1 minute, or give me a thumbs up if you're up till here. Okay, I see one person. Okay, so what I'm going to do is I'm going to click geometrical optics, and we have these different options underneath it. So first, what we are going to do is just click the geometric optics branch underneath the model. Okay, and then go to intensity computations. So it says none over here. So none is selected, but we're going to select compute intensity and power. If you want to compute power or intensity for certain projects that you want to work on, maybe you are doing any kind of concentration and you want to find out how much light got concentrated or what is the intensity or the power at that point. So this is where you basically put in your values, like put in your options, like do you want to compute intensity?
Can you show one more time how did you add the geometric optics?
I just click this one. Do you have geometric optics over here, right?
I didn't add it, like I missed something. I have the component ready. I don't have the geometric optics there.
Oh, okay. So then you can add so geometric optics is the physics that we are simulating, right? So
Oh, gotcha.
go
Yeah.
over here in physics.
Okay. Add physics.
And then to add physics. Okay.
Gotcha.
And then optics, ray optics, geometrical optics.
Oh, gotcha.
And if you do add to component one, it should add itself over here.
Okay.
Since we already did it before, we already have those.
Yeah, got it. Thank you very much.
Okay. I have to speed up a little bit over here so that I can at least finish the ray tracing. Okay, so now what we are going to do is look at the ray release and propagation window. So what this option, the maximum number of secondary rays, we're going to set it to 0. What does that mean physically? It means that suppose we have these primary rays that we're going to trace out throughout the system. And now if the system has certain reflections or scattering, it's going to create secondary rays, right? But in this case, we are just setting those to 0, which means that it's sort of like a special case that we are simulating just to reduce computation time and so on for now, because we are not worried about those rays, is that all the surfaces are not going to have any kind of extra scattering or reflection. So that's the secondary rays. So set that to 0. Okay. And then I'm going to click on material discontinuity, right? So the second option, which is here, and locate the coatings and set anti-reflective coating for the surfaces. So you see all the boundaries are selected, and these two tie in basically. So secondary rays having the value of 0 and material discontinuity having anti-reflective coat go hand in hand, so that you don't have any extra reflections or scattering. That's basically what that means. Okay, now what we are going to do is we are going to go into ray properties and select the wavelength. So we specified the wavelength inside our text file as 1.064 microns or 1064 nanometers. You can change it to any other. So this is not in the visible range, it's in the IR, but you can change it to 550 nanometers. That's green laser, green light. So I'm just going to, so we defined that value as LAM, or short for lambda, the wavelength. So I'm just going to type that in over here, LAM. Since I've already loaded the text file in my parameters, it's going to take the values from here. And I think I'll just put it in nanometers. Yeah. Wait, that's not needed. Okay. So I've specified the nanometers in the text file, I think. Yeah, okay. So that's redundant what I was doing. So remember, the default units for this problem is in millimeters. So any other unit that you want other than millimeters, you have to specify using these square brackets beside the value. And in this case, we have done it. We have written nanometers over here. In case this was not defined, the program would have taken the wavelength as 1064 millimeters. That's not what we want. So, but since the nanometers has been defined over here, it's going to override whatever unit it has when the program runs. Okay. Okay. Now what we're going to do is click on the physics toolbar over here and click global and do release from grid. So this is the Comsol's function for creating different rays. What it does is, suppose if you look at over here, it is a point source, but what it will do is it create this grid at this plane, and you will have points on that grid from which the rays are going to be released. In our case, it's just going to be one point from which a spherical ray is going to be released, right? So we have to first add that. So click physics, global, and then release from grid. So this is release from grid option has now been added under your geometric optics branch, right? So in the, there's these grid combinations that we can use, different types of ways in which the rays are going to be released, let's say. And what we're going to do is in the initial coordinates. So yeah, so this is 0, this is fine. And in the ray direction, we are going to choose conical. So what we'll see what happens, and then we'll see what the other options will be. And number of rays, the more number of rays you put in, the more number of rays will be used in the simulations, but it will take a long time and a lot of memory. So although the Comsol example uses 1000 rays, I'm just going to use 100 rays for now. And we want the cone axis to be pointed towards the y-axis. So we want y as 1 and everything else as 0. Okay. And the angle at which the cone angle is going to be pointed with respect to the y-axis, we have already defined it over here. And we are going to just put in that angle. That angle here is 0 degrees, but you can put in whatever, like it was set at pi over 3. So that, and the total source power, we have also defined that previously in this file as root mean square power of the source as I RMS or 1 watt. Although it is already 1 watt over here, let's just use the variable we have. Later on, we can change it to something else. So we'll just use IRMS over here. Okay. Now what we can do is, I think, although let's see. So this value, this button over here beside the initial coordinates, that sets the preview for where the rays are going to come out from, right? And so right now it's set here. I think, okay. Okay, so now I'm going to have to move this behind the first lens, right? Also, yeah, okay. Also, the other thing that we have to specify is that all the rays are going to get focused and get truncated at this plane. Otherwise, they are going to again diverge away from this plane. So we'll create a wall boundary that's going to stop all the rays at that plane. So in this physics toolbar again, in the boundaries, we'll click wall, and that's going to add a wall over here. And we'll just select this work plane like so. So if I click the work plane, it's going to add the work plane number 9 over here. And the wall condition is freeze. That means all the rays that are going to come and hit this wall are going to terminate at that point. They're going to end at that point. And that means that's it. So the rays won't propagate any further. Okay. So I'll wait maybe a few seconds at this point. And I'm going to add one last thing from the physics toolbar, that's attributes and deposited ray power. That's going to be added over here, which means that it's going to it's going to collect all the rays that are at this work plane. So see, all the other planes are not applicable because there's only one work plane, and that's been selected, number 9. And it's going to calculate all the deposited ray power over here. Okay. Then what else do we need to do before we can run it? Okay, so a couple of more things are left. So you see this materials branch has a tiny cross on it, which means we haven't defined any material boundaries. So that's remaining. So we'll right click that and do add, let's do blank material for now on. You can also do add materials from libraries, and that's going to open up this add material libraries, and it has all different types of glasses and metals that you can select from and add it to your simulation. For now, we are going to define a blank material, right? So it selected all the domains for the lenses. And it's asking for the refractive index, real part. We have already defined this, so n_r, and the imaginary part, n_I. So yeah, so that error has gone away. What else remains? Let's see. Right, so the last thing we'll do is create the mesh before running the solution. So this is finite element method analysis, which means it's going to discretize this region of space into tiny regions of space over which it's going to solve the equations that govern this specific system. And that's done by meshing this geometry. How do we do that? We click the mesh option over here on the left-hand side tree. So mesh 1. And what we are going to do is, let's see. Yeah, so mesh settings, we are going to set to extremely fine. And sequence type, we are going to do user control mesh. Why we are doing user control mesh, I'll show you. So what we want to do is we want to set a coarse mesh for the lenses and a very fine mesh for the work plane, which is this tiny square. Because if you keep the meshes same for both of them, either you will end up having a very fine mesh for the lens or a very coarse mesh for the work plane, which is not ideal. So we are going to right click on mesh 1 and do size. So it adds another size, and we're going to move this up. Okay, and this is going to define the size for the work plane. So select work plane. Yeah, so work plane, and I'll do custom over here. Sorry, custom over here, and I will use these two maximum and minimum element sizes to define what I want as the very, very fine mesh for this work plane, and then do build all. So it completed meshing very quickly. You can see for the lens, which has been meshed, it's much coarser compared to the work plane, which is much finer meshed. So see, it's much finer compared to the lenses. Okay, that's good. And lastly, I know I'm just speeding up a little bit over here, but this will be recorded again. So if you are stuck, you want to, and the video will be uploaded today evening. So just go back to the video and just rework your problem. Just save it at one point if you want, and rework the problem. If you have any questions, let me know. So other than that, so we'll just click study 1 and go to bidirectionally coupled ray tracing. And it gives us some options by which we can specify how long the study is going to run. So we can do time steps, or we can do maximum path lengths. So I'll select maximum path lengths and choose the units as millimeters, although it's going to override anyways, and choose the range of ray path lengths that are going to be simulated. You could do this using time steps, but in this case, since the length dimensions are sort of known to us, that's what we're going to use for now. So I'll put in certain values of the path lengths that I know is sufficient enough to complete this simulation. And again, you can later on change these ranges and see how it affects the simulation. Right? So I'm just going to put in 2 ranges. Right? Okay. I think that should be good enough. You could change this to something else. You could do like 10 millimeters and see what happens. The rays will propagate 10 millimeters from the source and so on. Okay, and I think that's it. What is left? Let me just check. Oh yeah, so one more thing is number of iterations. I'll just lower it down to 3 for now. That's the number of iterations for the solver. Otherwise, it's fine. Okay, so on the study toolbar, we are going to use show default solver. Let's see. It's quite a few steps actually. Yeah, so here's the solver that we are going to use. And so over here, we are going to go into dependent variables. And it looks okay. I don't think we have to change anything over here. Yeah, I think this is fine. I think it's supposed to run properly and trace the rays. I'm just going to save it now, and maybe in the interest of time, compute and see what I get. Usually there's a couple of errors sometimes, and we have to fix it, but this would be how you progress through the problem. And then usually for most simulations, you end up with some bugs or some errors that you have to later fix. So while this runs, I'm going to show you something interesting. So one good thing about Comsol is it has so many things. You saw that there's so many things that you need to program in that sometimes it gets confusing. So one great thing that they have is this examples library. So if you just Google for Comsol ray optics examples, you have these different examples that you can look into and learn from there. That's sort of the best way by which you can learn. So like open up one of the examples which looks good for your project, like solar concentrator or lenses and so on, and then just run through that example, practice it by yourself, change certain values. And so if one of you guys are working on daylighting, there's one example for light pipes over here. So you can look at that. I see here the transparent light pipe. So lots of different examples that they have over there. So I think, okay, so it did simulate the rays, but I think there might have been a little bit of a problem with where I had placed the source. So I needed to place the source. So for some reason, the source got placed in between the two lenses. But that's, I guess that's something, if we fix it, it's going to trace the rays correctly. But yeah, so that's what you, basically that's the steps that you want to do to simulate rays and certain geometries. And then that's basically how you solve one of the geometric optics problems using the software. But yeah, it's got many different aspects, and the best way I think to learn would be to go through these different examples, select the one that best suits your needs, and then try to run it, try to change it according to your needs. And then if you have any questions, get back to me. I can help you solve your problems easily. Other than that, I will just maybe try to debug this a little bit, and the solution will be uploaded today. Okay, so that's all I have for now. I think maybe we are running a little bit over. So Dr. Menon, it's over to you. Let me see what I did over here.
Yeah, I think I'm still here, sorry. We are pretty much good to go since we're almost out of time. So if there are any quick questions, we can address them, but otherwise we can stop today. I will make a point that this will be recorded
just
and
something
posted
to add
later today.
Yeah, I just found that when I was going through the problem, I missed out where I had to correctly input the y-axis location for the ray source. I kept it at 0. That's why it sort of didn't work. But so once that I updated it, it simulates it correctly. So you can see the point source, and the rays become parallel after the first lens, and then they go to a focus after the second lens onto our work plane. It's basically the solution to this problem. Okay.
Right. So just remember to review this video when it's posted later today. And on Thursday, we'll have a very similar sort of discussion with light tools in Code 5. And if everything is set up, I will send the instructions on how to run them. We're still trying to do that. So if it's not posted, that means you will have to run them later on.
Right. So one quick thing that I wanted to add, this is something they have added this year. I saw this very nice compact camera module simulation that they have done. It uses these different types of lenses that are inside, suppose your DSLR lens or your iPhone camera, and it ray traces through all these different lenses. This is similar to, I think, what Code 5 can also do. So Comsol is really good.
The two different options, yeah.
Yeah.
So some of you may be familiar with or prefer one over the other. So think of these as different tools. Okay. All right. And, post your questions on Slack as before. Okay. If there are no more questions, let's end here today. Thank you, Aputam. Thank you, everyone.